Hello everybody, welcome to the second part of Game Theory in a Nutshell. You have to watch the first part before watching this, otherwise you will not understand much. Having discussed the game V&M Poker 3423, its extensive form, information sets and the 8 strategies of Anne and Beth in the first part, in this part we will move to the normal form, we will eliminate weakly dominated strategies and then find a Nash equilibrium in mixed strategies. Even though we still play the same sequential game when both players choose a strategy in advance and submit it simultaneously to a referee, the form of the game now has changed considerably. No on-site playing is necessary anymore. The referee just performs an experiment, simulating the behavior of the players using their communicated strategies. So we essentially have arrived at a simultaneous game with randomness. These expected payoffs are collected in a table which we call the normal form of the game. The rows are labeled by all pure strategies of N and the columns are labeled by all pure strategies of Beth. In the corresponding cell we write a pair of numbers, the expected payoff for N and the expected payoff for Beth. In case of a zero-sum two-player game, where one gains what the other loses, it suffices to display N's payoff as Beth's payoff is just the opposite of that. Here's the skeleton of the normal form. We have 8 rows and 8 columns. Let's now show the calculations required to put in the values. We assume that both Anne and Beth have a strategy chosen. Let's say Anne plays CRR and Beth plays FFC. We go to the extensive form and hardwire the decisions of the players in. We have a C for checking in Anne's first information set. Anne raises in her second information set. And also in her third one. Beth folds in her first, the yellow information set. She also folds in the information set having a queen, which is colored in brown. But in her third information set, colored in green, she calls. You have to look carefully to see the difference. What we cannot predict are the random moves. So let's say we pump water through the extensive form. Water will flow only through the hardwired moves of Anne and Beth according to their submitted strategies, but also through all branches at random moves. Water will arrive only at some of the possible outcomes, shown here. The probability that the play ends in such an outcome is, in our case, just the probability of the one random move taken to reach that point. In case of more random moves, it is a product of the probabilities of all random moves taken in order to arrive there. All what remains to be done is to do the expected value calculation for N's payoff in these outcomes. We multiply the probability of the first random move, 3 over 33, with N's payoff at the outcome the water arrives when following this way, 0. We also multiply 4 over 33 and negative 2. Proceeding this way, we get 9 products. We add all these numbers and get a value of 2 over 33, which is Anne's expected payoff, provided Anne plays CRR and Beth plays FFC. Of course, now we could do the same for Beth, but as this is a zero-sum game, Beth's expected payoff is just the opposite of Anne's expected payoff. We write these two numbers into the corresponding cell in the normal form. Let me now do just another example without words. Looking at it, can you answer which strategy you would play, as N or as Beth? Or could you even tell how they should play? This is not so easy, but we certainly have a few candidates that we should not play. Playing the strategy RRC might look silly to you. Why? Well, because why would you check with a king if you even raise with a jack or queen? Or maybe even stronger, why would you check with a king anyway, since you cannot lose in that case? In the same way, folding with a king is a silly thing to do for Baz. A more formal reasoning for this uses the weak domination concept for simultaneous games. Strategy CCC is weakly dominated by strategy CCR. We look at Anne's payoffs in the rows corresponding to Anne's strategy we want to compare. Whatever Baz does, Anne's payoff is at least as high with CCR than with CCC. In the same way, CRR weakly dominates CRC, RCR weakly dominates RCC, and RRR weakly dominates RRC. So we are left with 4 strategies for N. In the same way, strategies FFF, FCF, CFF, and CCF, everything where Baz folds with a king, are weakly dominated. For Baz strategies, we look at Baz payoffs and we compare columns. A little surprisingly, there is one more weakly dominated strategy so. Strategy FCC weakly dominates strategy CFC. Baz should never fold with a higher card if she calls with a lower one. After eliminating weakly dominated strategies, we arrive at the following smaller bimatrix. The next tools from our simultaneous games toolbox are best response, and Nash equilibria. For instance, Baz's best response to Anne's RCR is CCC, Anne's best response to B's CCC is CCR or CRR, Baz's best response to Anne's CCR is FFC, Anne's best response to Baz's FFC is RRR, Baz's best response to Anne's RRR is FCC, Anne's best response to Baz's FCC is CCR, but we have been there already. We are running in circles. In fact, and unfortunately, the game does not have a Nash equilibrium, in pure strategies at least. So we need to proceed to mixed strategies. Looking closer on the smaller normal form, with weakly dominated strategies removed, you might notice that the game is to the advantage of N. With one exception, N has non-negative payoffs in these 12 outcomes. So shouldn't N be able to guarantee a positive outcome? Not with a pure strategy. The minimum in every row is 0 or even negative in the 4th row, so is a guaranteed payoff. The guaranteed payoff for N is 0, and the maximum pure strategies are CCR, CRR, and RCR. However, you might also notice that the weakness of the strategies appear at different columns. For instance, RCR is weak against CCC, but CCR is strong there, while CCR is weak against FFC, against which RCR is very strong. And against FCC, both CCR and RCR are kind of okay. Now the idea of mixed strategies help. Why not combining 2 or more strategies and playing them randomly, but with given probabilities? If N would just randomly choose CCR or RCR with equal probability each, how would such a mixed strategy perform? Let's add this mix under N's options and let's calculate the expected payoff against Baz's pure strategies. 1/2 times 0 plus 1/2 times 0.55 is about 0.27. 1/2 times 0.12 plus 1/2 times 0.06 is about 0.09, and 0.12 for the third entry. So, if N is allowed to choose among her 4 pure strategies and just this one mixed strategy and no others, this mix described would certainly maximize her guaranteed payoff, and this mix would be her maxi-min move. However, N might look for even better mixes. Since this 50-50 mix is weakest against FCC, we might have to use more CCR, which is strong there, and less of RCR. We will later see how to best change the recipe. But Baz might also start mixing strategies. If we open the can of mixed strategies, things get even more messy, because there are suddenly infinitely many mixes, infinitely many strategies for both players. Now, John Forbes Nash showed in 1950 that every game has some, how we call it nowadays, Nash equilibrium, if we allow mixed strategies. Such Nash equilibria are usually notoriously difficult to find. Only in case of two-player zero-sum games, linear programming can be used, which makes life much more easy. But even that is too complicated for this short and simple video. So, how can we find such Nash equilibria in mixed strategies fast and easily? There's one method which, although not working always, works well enough in most cases. This is G.W. Brown's fictitious play. We assume that two players play over and over. N keeps track of all strategies of Baz played so far, and at each round N plays a strategy that is the best response to this observed mix of the whole history. But the same for Baz. Since both respond always to what they observe from each other, their strategies always might change. But since the observed history gets longer and longer, each new change affects the history less and less, so the observed mixes change, but they change slower and slower. The hope is that these mixes eventually get closer and closer to the Nash equilibrium mixes. This is called Brown's fictitious play because the players do not actually have to play over and over. It's sufficient if they imagine it. Let me explain it in an Excel sheet that I created. Here's a normal form with all weakly dominated moves removed. The yellow cells contain the history, and in the gray cells are the percentages observed. This row is dedicated to N's observed mix so far, and this column to Baz's observed mix. The values are the expected payoffs of the mixes against the corresponding pure strategies. You see that N played CCR in the first round and Baz played FCC. N therefore plays CCR in the second round and Baz plays the best response to CCR, which is FCC. Now, N assumes that Baz plays a 50-50 mix of FFC and FCC. Here are the payoffs of the observed mix. N's best response to this mix is RCR, with an expected payoff of 0.222. Baz plays FFC again. After a few rounds we arrive here. N's mix is heavier on CCR and Baz's mix is even heavier on FCC. N's best response to what she observed from Baz so far is another CCR with an expected payoff of 0.113. Baz's best response to what she observes from N is another FCC with an expected payoff of negative 0.107. And so on. You see that the percentages in the mixes still change after all this time, but they change less and less. We arrive at a mix of 80% CCR and 20% RCR for N, and a mix of 10% FFC and 90% FCC for Baz. These mixes form a Nash equilibrium and the expected payoff for N is 0.109. If we translate this Nash mix, it means that N will raise with a check in 20% of the cases, so the bluffing, and check otherwise. N will never raise with a queen, never ever, and N will always raise with a king. And Bears will always fold with a jack, always. Bears will call with a queen in 90% of the cases, otherwise fold. And Bears will always call with a king, always.